Good day everyone and welcome to part 2 of our discussion on chemical thermodynamics. In the previous lesson, we focused more on the technical aspect of thermodynamics and how it was applied to calorimetry. For this second part of the lesson, we will now be focusing on how does energy blend into our calculations for chemical reactions. So let's begin. Before we go any further, it is important that we first understand what are thermochemical equations. These types of equations are basically the same as our chemical reactions. You have here your reactants and your products. However, we are integrating your delta H term or your change in enthalpy term as part of the chemical reaction. So there are a couple of things to notice about a thermochemical equation. First is the stoichiometry. In our past lesson on reaction stoichiometry, I have mentioned to you that it's important to balance your chemical equation before you can proceed with stoichiometry. Because let's say, for example, in this equation, 1 mole of C2H5OH is equivalent to 3 moles of O2. That's also equivalent to 2 moles of CO2 and equivalent to 3 moles of H2O. The same is true for thermochemical equations because the value of delta H here can also be used for stoichiometry. Meaning 1 mole of C2H5OH, if you reacted this with 3 moles of oxygen, the reaction would give off 1,367 kilojoules of energy. So how do I know that the reaction would give off energy? I got that from the sign of the delta H from the thermochemical equation. That is another thing that you have to look out for when you are given a thermochemical equation. Take a look at delta H, take a look at the sign, and that should give you an idea if the reaction is exothermic or endothermic. Since our delta H here is negative, meaning energy is being given off, that means that this equation or this chemical reaction is exothermic. As further supporting evidence of my earlier point that you can use a thermochemical equation for stoichiometry, take a look at our example at the bottom. This is the same chemical equation as the one given at the top. However, in this second instance, your delta H is given as parts of the products. We have already discussed this earlier. If your heat term is part of the products, that means that it is being given off. That's why your delta H in the above equation is negative. So these two equations are basically the same equations and they are called thermochemical equations. Let's try to solve this example. When 2.61 grams of dimethyl ether or CH3OCH3 is burned at constant pressure, 82.5 kilojoules of heat is given off. Find delta H for the reaction. CH3OCH3 plus 3O2 yields 2CO2 plus 3H2O. This equation is already balanced, so we can proceed with this stoichiometry. This is just a problem in stoichiometry, no? We are just incorporating the concepts of thermochemistry. So let me first write the given. Again, you are given the chemical reaction here. We are tasked to solve for the delta H of the reaction. Our only given is that we have 2.61 grams of CH3OCH3 and then the reaction of that amount gave off 82.5 kilojoules of heat. So from the term gave off heat, that gives us a clue that our Q in this case is negative. That's why I have written here that Q is equal to negative 82.5. If you will go back at the problem did not state that 82.5 kilojoules is negative. So there was no direct indication that this is negative. However, it has stated that this amount of heat is given off. So based only on the wording of the problem, you have to decide whether to place a negative sign or not on this heat. In this case, it's given off, meaning it's being released. So we have to place the negative sign on our Q. Okay, our solution to this problem is very straightforward. When you are solving for the enthalpy of the reaction, you simply imagine what are the units of the enthalpy of reaction. The normal units of enthalpy of reaction is either joules per mole or kilojoules per mole. Now, if I'm giving you the chance to choose whether you want to use joules per mole or kilojoules per mole, you might want to use kilojoules per mole because your Q is already given in kilojoules. So there's no need for us to convert. And then taking a look at the units of delta H, we can deduce the formula that we are going to use to solve for delta H. So kilojoules is the unit of heat, and heat is denoted as Q, while the bottom unit is moles, and that directly pertains to the number of moles of the substance that was being reacted. Okay? So that means that we only need to convert 2.61 grams of CH3OCH3 to the number of moles of CH3OCH3 and substitute that to our deduced delta H reaction equation, and then we have already solved the problem. Okay? All problems are very easy if you know how to deconstruct the problem. So let's convert the grams of dimethyl ether to the moles of dimethyl ether. So from 2.61 grams CH3OCH3, we need to divide this by the molecular weight of CH3OCH3. Carbon is 12.011. Multiply that by 2 because we have 2 carbons. Plus hydrogen is 1.008. Multiply that with 6 and then plus 1 oxygen. That's 15.999. The molecular weight of dimethyl ether is 46.069. So we divide by 46.069 grams of dimethyl ether. That's equivalent to 1 mole of dimethyl ether. Dividing, we have 2.61 over 46.069. The answer is 0.0567 moles. We are retaining 3 significant figures. And then we substitute this to our delta H equation. We now have Q is negative 82.5 kilojoules and the number of moles is 0.0567 moles. We now have solved for the delta H of the reaction. That is negative 82.5 divided by 0.0567. Our delta H reaction is negative 1460 kilojoules per mole. So that is 3 significant figures. That is how we solve stoichiometric problems involving the enthalpy of reaction. Let's proceed. Okay, another example. When aluminum metal is exposed to atmospheric oxygen, it is oxidized to form aluminum oxide. How much heat is released by the complete oxidation of 24.2 grams of aluminum at 25 degrees Celsius and 1 atmosphere? The thermochemical equation is given below. That's 4 aluminum plus 3 O2 yields 2 Al2O3. And we are given the enthalpy of the reaction as negative 23,352 kilojoules per mole. Now, our approach to this problem would be similar to our approach to the previous problem, and we will be treating this as a problem on stoichiometry. The problem is asking how much energy in the form of heat will be released if 24.2 grams of aluminum is completely oxidized. Again, we start with the given 24.2 grams of aluminum, and we simply perform our stoichiometry. So the molecular weight of aluminum is 26.982 grams of aluminum per 1 mole of aluminum. And then based on the balanced equation, for every 4 moles of aluminum, we have negative 23,352 kilojoules of energy that can be released. So that is the convenience that the thermochemical equation gives us. We can directly convert from the amount of moles of a substance to the amount of energy. Take a look at the cancellation of units. Grams of aluminum, moles of aluminum, you will be left with the unit of kilojoules. And that's what will give you assurance that your solution is correct. So calculating, we have 24.2 divided by 26.982 times negative 23,352 kilojoules. Our answer for Q, negative 20,900 kilojoules of energy. This is rounded to 3 significant figures. Okay, so you just have to revisit your stoichiometry and apply thermochemistry. Let's proceed. Now let's talk about standard states and standard enthalpy change. The concept of the standard enthalpy change is very important for us because it gives us a baseline from which we can compare different substances and their differences in energies. And for that, we have to learn about the standard states. The standard state of a substance is its most stable form at 298 Kelvin and 1 bar. Basically, it's the phase of the substance at 298 Kelvin and 1 bar. For example, water. If you are asked, what is the standard state of water? If you take a look at water existing at 298 Kelvin and 1 bar, essentially atmospheric pressure, we see that water is a liquid because basically this is room temperature. Therefore, we say that the standard state of water is liquid. This will be very important for thermochemical equations because from now on, you need to specify the phase or the states of your substances. Because a difference in states could mean a difference in the value of the standard enthalpy change of the reaction. You will see that later with water because water has a different value for the enthalpy of formation if it is a gas and if it is a liquid. Here are some guidelines on how you can determine the standard state of substances. For pure solids and liquids, the standard state is the pure solid or liquid form. So an example of this is water, no? It's a pure liquid at room temperature, therefore its standard state is liquid. Another example is aluminum. At the standard condition of 298 Kelvin in 1 bar, aluminum exists as a solid. For pure gases, the standard state is 1 bar of the gas, and for gas mixtures, the standard state is partial pressure of 1. We will again be using our knowledge of the diatomic elements because their standard state is their diatomic form. So let's say, for example, what is the standard state of oxygen? Its standard state is diatomic oxygen gas because at room temperature and atmospheric pressure, it exists as a diatomic molecule and it is a gas. I will be guiding you with the standard states in our next examples. Now let's discuss the standard molar enthalpy of formation. We define this as the enthalpy change for the formation of 1 mole of a substance from its constituent atoms in their standard states. Now that might be difficult to understand, so just take a look at these examples here. For the first example here, we have hydrogen gas plus bromine liquid yields 2 HBr gas. Enthalpy of reaction is negative 72.8 kilojoules per mole. Now take a look at the second example. For the second example, it's basically the same reaction, but it has different coefficients. It's now 1/2 hydrogen gas plus 1/2 bromine liquid yields HBr gas. Enthalpy of reaction, that's negative 36.4 kilojoules per mole of the reaction. The second equation is what we call a standard molar enthalpy of formation reaction. We say that this is the standard molar enthalpy of formation of hydrogen bromide because the product is only 1 mole and the reactants are all elements in their standard states. So for a thermochemical equation to be a standard molar enthalpy of formation reaction, it has to satisfy 3 criteria. The first criteria is you should only have 1 product. In this case, we have 1 product. The second criteria is that all of your reactants should be elements in their standard state. So hydrogen, standard state is gas, check. Bromine, standard state is liquid, check. And then the last criteria is that when you balance your chemical reaction, your product should only have a coefficient of 1. And that's what separates the first equation from the second equation. The first equation is not a standard molar enthalpy of formation reaction, but the second equation is a standard molar enthalpy of formation reaction because it satisfies our 3 criteria. Only 1 product, its coefficient is 1, and then all of your reactants are elements in their standard states. Therefore, under these conditions, the enthalpy of reaction of a standard molar enthalpy of formation reaction is also the heat of formation of the product. In this case, the enthalpy of formation or the heat of formation of hydrogen bromide is negative 36.4 kilojoules per mole. Now, you don't need to memorize this enthalpy of formation values for the substances because there's too many. I will be giving you a value of this. So, noted in this table are some standard molar enthalpies of formation of the substances. So, there's a few things to note in this table. You can see that some entries are 0, and you can see that some entries have values. So what does it take for your standard molar enthalpy of formation to become 0? This is a very important skill for you to develop because deciding which will become 0 will be important in problem solving. Notice that all of the entries that have 0 as their values are all elements in their standard states. Therefore, if you see an element in its standard states, its enthalpy of formation is automatically equal to 0. Okay? Now, take a look at the 2 entries for bromine. The first entry for bromine is liquid. The second entry for bromine is gas. They are both diatomic, so they are just differing in their phase. One is liquid and one is gas. But take a look at their enthalpy of formation values. The enthalpy of formation for liquid bromine is 0, while the enthalpy of formation for gaseous bromine is 30.91 kilojoules per mole. What does that mean? That means that bromine under standard conditions exists as a liquid because only elements in their standard state can have an enthalpy of formation of 0. Everything else will have a value. Okay? Another example of that is carbon. If you take a look at the table, we have two entries for carbon. The first entry is diamond, which still is carbon. The second entry is graphite. Diamond has a value for the enthalpy of formation, while graphite has 0 for the enthalpy of formation. That means that the standard state of carbon is graphite. It's solid and it exists as graphite. Okay? So please remember that for all elements in their standard states, their enthalpy of formation is 0. Let's try this example. The standard molar enthalpy of formation of ethanol, C2H5OH, is negative 277.7 kilojoules per mole. Write the thermochemical equation for the reaction for which the enthalpy of reaction is negative 277.7 kilojoules per mole reaction. Now, the most important thing to note in this example is that we want to know what is the chemical equation that will satisfy the enthalpy of reaction being equal to the enthalpy of formation of ethanol. That means that we are looking for the standard molar enthalpy of formation reaction of ethanol, because that is the only way wherein we can have the same enthalpy of formation with the enthalpy of the reaction. Okay, so what this problem is asking us is it wants us to write the standard enthalpy of formation reaction for ethanol. So I will be teaching you how to construct a standard molar enthalpy of formation reaction. For the construction of standard molar enthalpy of formation reactions, we start with the product. Remember that one of our criteria for standard molar enthalpy of formation reactions is that you only have one product and the coefficient of the product is 1 mole. So in this case, our product is ethanol, C2H5OH, liquid, and its coefficient is 1. If you will remember, another criteria of standard molar enthalpy of formation reactions is that your reactants are all elements at their standard states. So take a look at your product and then enumerate all of the elements that you can see. So for ethanol, we have 3 elements, that is carbon, hydrogen, and oxygen. The next step is you need to think of what are the standard states of these elements, and this will be your reactants. For carbon, as we have discussed earlier, its standard state is solid and it is the graphite form. This serves to differentiate between carbon from graphite and carbon from diamond or carbon from any other allotrope. Okay? Next is hydrogen. What is the standard state of hydrogen? If you will remember, hydrogen is one of our diatomic elements. Have no fear on ice-cold beer. It's at the very top of the list. So therefore, the standard state of hydrogen is H2, gas. And oxygen is also part of our have no fear on ice-cold beer. So the standard state of oxygen is O2, gas. So now that we know the standard states of your constituent elements, you can now place them in the reactant side of the reaction and then balance the equation. So let's start with carbon. Carbon, solid, graphite. How many carbon do we need? We need 2 because ethanol contains 2 carbon. Next is hydrogen. H2, gas. How many hydrogen do we need? Ethanol contains 6 hydrogen atoms. Therefore, to balance, we multiply this by 3. And then finally, oxygen. O2, gas. How many oxygen atoms are in ethanol? We only have 1. So to balance, we need to multiply O2 by 1/2. And this is our standard molar enthalpy of formation reaction for ethanol. You see that it's a balanced equation and it satisfies our 3 criteria. Again, the first criteria is you only have one product. The second criteria is the coefficient of your product is 1. And the third criteria is all of your reactants are elements in their standard states. Therefore, we can now say that the enthalpy of reaction of this standard molar enthalpy of formation reaction is equal to the standard enthalpy of formation of ethanol. And the value of that is 277.7 kilojoules per mole. Okay? So that is how we write standard molar enthalpy of formation reactions. Do not forget our three criteria. Okay, let's move on. We are now nearing the end of our lesson. So we will be discussing Hess's law. Hess's law is a very convenient way for us to determine the enthalpy change of a chemical reaction simply by using the enthalpy of formation of the reactants and the products. Okay? If you will go back to our definition of an enthalpy change, delta H, enthalpy is a state function. Therefore, we only need to know the final enthalpy and the initial enthalpy in order for us to get delta H. In this case, the final enthalpy represents the enthalpy of the products. Hence, you have here the enthalpy of formation of the products. And the initial enthalpy is represented by the enthalpy of the reactants. Therefore, Hess law is simply the summation of the coefficients in the balanced equation multiplied by the enthalpy of formation of the products minus the summation of the coefficient in the balanced equation times the enthalpy of formation of the reactants. A very easy way of remembering Hess law is it's always products minus reactants. Let's try to solve some examples. Calculate delta H reaction for the following reaction at 298 Kelvin. That's SiH4 gas plus 2O2 gas yields SiO2 solid plus 2H2O liquid. So let me first write this reaction. This is a classic problem involving Hess's law. No? We are required to solve for the enthalpy of the reaction, but we are just given a balanced chemical equation. For these types of problems, we have to look for the enthalpy of formation values for each of the reactants and the products, and then apply Hess law to determine the enthalpy of reaction. So let us look for the values of the standard enthalpies of formation of all of our components in the chemical reaction. But before we do that, take a look at your equation first and decide whether some terms should be zero. If you will remember, for all elements at their standard states, their enthalpy of formation is zero. Take a look at your components. We have SiH4, oxygen, SiO2, and 2H2O. We only have one free element here, and that is oxygen. Let's see if it is at its standard state. It's O2 gas. It is at its standard state. Therefore, automatically, its enthalpy of formation is 0. Therefore, we only need to find for three values of the enthalpy of formation. If we take a look at our given table, we are looking for SiH4, so it's here. The value is 34 kilojoules per mole. For SiO2 solid, we have negative 910.9 kilojoules per mole. And finally, for water liquid, if you take a look at the entries for water, you have a liquid and a gas. That's why it's very important for you to determine the exact phase of water because the values are different for liquid and gas. In this example, we need the value for the liquid, so that is negative 285.8. Okay, let's go back. I have now listed the enthalpies of formation of our substances. So let's apply those to Hess's law. Hess's law states that the enthalpy of reaction is equal to the summation of the coefficients multiplied by the enthalpy of formations of the products minus the summation of the coefficients multiplied by the enthalpy of formation of the reactants. It's products minus reactants. So, on our product side, we have two terms. That's from SiO2 and from H2O. You simply multiply the value of the enthalpy of reaction to the coefficient in the balanced equation. Again, before you proceed, make sure that your equations are balanced. Okay? So for SiO2, its coefficient is 1. So we write 1 times negative 910.9 plus for water, that is 2 times negative 285.8. This is now your value for the product side. From this, we subtract the values from the reactant side. On your reactant side, you have two components, SiH4 and oxygen. However, oxygen is 0 because it is an element at its standard state. Therefore, we will only use SiH4, and that is 34. 34 times 1. And then we simply compute to get the enthalpy of reaction. That is negative 910.9 plus 2 times negative 285.8 minus 34. Our enthalpy of the reaction is negative 1516.5 kilojoules per mole. Okay, so it's very easy to apply Hess law as long as you have values for the standard enthalpy of formation of your reactants and your products. In the exams, you will be given all of these values, so don't worry, you don't have to memorize them. What you just need to know is how to apply Hess law in these types of problems. For this second problem, I want you to practice on your own. Use the following information to determine the enthalpy of formation for lead oxide solid yellow. You're given the chemical reaction lead oxide plus carbon monoxide yields lead plus carbon dioxide. In this case, you are given the enthalpy of reaction. That's negative 65.69 kilojoules. However, you need to determine the enthalpy of formation of one of the reactants, and that is lead oxide. So this would entail some algebra, but nevertheless, you would still be using Hess law. Okay, so try solving this problem in order for you to apply your learnings. Okay, next. This problem is a variation of Hess law. Instead of us searching for the enthalpies of formation of each component of the chemical reaction, we are going to use other chemical reactions and their enthalpies of formations to determine the enthalpy of reaction of an unknown reaction. So example, use the thermochemical equations here below to determine the enthalpy of reaction at 25 degrees Celsius for this reaction. That is carbon in the form of graphite plus 2 hydrogen gas yields methane gas. If you will notice, this chemical equation bears resemblance to the chemical equations given below. The problem here is we want to know the enthalpy of reaction for this first equation, but we are only given these three equations with the given enthalpies of reactions. So our technique here would be to rearrange these three equations such that if I add them together, the resulting equation would be our unknown equation. So how can we do that? You can either flip the reaction. When I say flip the reaction, your reactants and your products will switch places. What that does is that will reverse the sign of your delta H. So let's say, for example, if I flip the first equation and make it CO2 yields carbon plus oxygen, the delta H for that equation will now be positive 393.5. Okay? That's called flipping the reaction. Another thing that we can do to achieve our final reaction is that you can multiply these equations by factors so that they can cancel out. I will show that to you later. But basically, if you multiply a certain equation by a certain number, you not only multiply the numbers to the coefficients in the balanced equation, but you also multiply the factor to the value of the delta H. I will show you that in this example. So let's begin by listing all of these reactions. Okay, here's our technique for these types of problems. First, take a look at your unknown equation. So our unknown equation is at the top, that is carbon plus hydrogen yields methane. What we are going to do is we will analyze this equation one component at a time, and then we will take a look at the placement of that component if it's correct. Let's say, for example, for carbon. For carbon, it was only mentioned in the first equation here. And if you take a look at their placements, carbon in our unknown equation is on the reactant side, and the carbon on the first equation given here is on the reactant side. So that is already correct. You don't need to flip the equation. Next, we take a look at the coefficient. The coefficient of carbon in our unknown equation is 1, and the coefficient of carbon in the first equation here is also 1. Thereby, we no longer need to multiply this equation by a coefficient. So the first equation will stay as it is. Okay? So we're done with carbon. Next, hydrogen. In our unknown equation, we have 2 moles of hydrogen gas. If you take a look at the equations below, hydrogen exists at the second equation in the reactant side. So they are both in the reactant side, so no need to flip the equation. However, in your unknown equation, hydrogen has a coefficient of 2, and in the equations below, hydrogen has a coefficient of 1. Therefore, to balance that, you need to multiply this entire equation by 2. And if you multiply an entire equation by 2, you also need to multiply its enthalpy of reaction by 2. Okay? So let's multiply this equation by 2. We now have 2H2 plus 1O2, because 1 half times 2 is 1, yields 2H2O. Okay? We have multiplied the entire equation by 2. We are done with hydrogen. Last one, methane. Methane exists in the products in your unknown equation. But in the equations below, methane is on the third equation and it is on the reactant side. So what you need to do is you need to flip the third equation such that methane will be on the product side. Okay? We no longer need to multiply the third equation because the coefficient of methane is 1. So let's flip the third equation. And by the way, by flipping the third equation, that changes our enthalpy of reaction from negative to positive. So our enthalpy of reaction is now positive for the flipped reaction. Okay? Okay, so flipping the reaction, we have CO2 gas plus 2H2O liquid yields CH4 gas plus 2O2 gas. Okay, so just a quick recap. Our first equation was not changed. The second equation was multiplied by 2. And the third equation was simply flipped. So you can see the effect of those changes on the delta H of the reactions. Okay, for the moment of truth, we need to add your 3 reactions. And our final reaction should match our unknown reactions. So just a quick tip for adding reactions. If a component or if a species appears on the reactants and on the product side of separate reactions, they will just cancel out. Okay, let's first search for components that will cancel out. So take a look at carbon dioxide. On the first reaction, carbon dioxide is on the product side. And on the third reaction, carbon dioxide is on the reactant side. That is 1 carbon dioxide minus 1 carbon dioxide. That simply cancels out. Okay? What else can we cancel? Let's take a look at oxygen. First equation, you have 1 oxygen on the reactant. Second equation, you also have 1 oxygen on the reactant. Total of 2 oxygen molecules on the reactant side. And on the third equation, you have 2 moles of oxygen on the product side. So those all just cancel out. Last one, water. Let's take a look at water. For the second equation, you have 2 moles of water on the product side. On the third equation, you have 2 moles of water on the reactant side. That again cancels out. We no longer have things to cancel out, so let's add the remainders. So we now have carbon, graphite, plus 2H2 gas yields CH4 gas. Now the question is this resultant equation the same as our unknown equation? The answer is yes. They match. Therefore, if I add the enthalpies of reaction of my modified equations, that should give me the enthalpy of reaction for my unknown reaction. So let's try to add. That is negative 393.5 plus negative 285.8 times 2 plus 890.3. The answer is negative 74.8 kilojoules per mole. That is the enthalpy of reaction for our unknown reaction. Okay? So this is just a variation of Hess Law. Again, you just have to modify your equations by flipping or by multiplying a factor just so that you will arrive with the unknown equation. And then if you add all of the enthalpies of reaction, you arrive with the enthalpy of reaction of the unknown equation. Now, how do we prove that we have gotten the correct enthalpy of reaction? If you'll notice, Our resulting equation is actually a standard molar enthalpy of formation reaction. Why? Because you only have one product, that's methane, its coefficient is 1, and your reactants are both elements at their standard states. Therefore, we can also say that the enthalpy of formation of methane is negative 74.8 kilojoules per mole. Now let's check if the enthalpy of formation of methane is really negative 74.8. Let's take a look at our tables. This is our table for the standard molar enthalpies of formation. For CH4, that is negative 74.81. That's close enough. Okay? Meaning that we are correct in our solution. That is how we apply Hess law. That is how we take advantage of the enthalpies of reactions of other reactions to come up with the enthalpy of reaction of another reaction. Okay? For the remaining examples, such as this one, I want you to solve this on your own. So you only have two known equations and you want to modify this in order for you to arrive with this final equation. Try solving that as your practice. And that's the end of this lesson. Again, please watch out for another video detailing these solutions for more practice problems, and that will serve as your reviewer for the upcoming module exam. Thank you for listening. I hope you have learned something. If you have any questions, don't hesitate to reach out. And as always, keep safe.